Children, the reason why we talked about overall dipoles of a molecule, or dipole moment of a molecule, is because only if you have an idea about this dipole moment or the overall dipole moment of a molecule, okay, only if you have a very, very clear idea about dipole moment of a molecule, we can go to our next part of the lesson. The next part is about intermolecular attractive forces. You can't talk about intermolecular attractive forces if you don't know anything about dipole moments in a molecule. What is the meaning of intermolecular attractive forces? As the name suggests, intermolecular attractive forces are found between molecules, intermolecular, between molecules. We'll read this a little bit. Intermolecular attractive forces are quite different to covalent, ionic, and metallic bonds. Those are main bonds, but then intermolecular attractive forces are not those things. Intermolecular attractive forces are formed between covalent molecules in different forms, according to their nature of polarity. There are few intermolecular attractions. Just go through the first one. Van der Waals or instantaneous dipole, induced dipole attractions. Within bracket, we can write ID dash ID. First ID means instantaneous dipoles. Second ID means induced dipoles. ID attractive forces. They also have another name, temporary dipole attractions. Okay, what are the names? Van der Waals forces. We discussed instantaneous dipoles, induced dipole, the same thing. Temporary dipole is the same thing. Second one is permanent dipole. You can open up a bracket over here and write permanent dipole attractions are PD. Earlier ID. Now PD. Permanent dipole attraction. And we have hydrogen bonds. We are going to discuss about first one, second one, and third one, but not fourth and fifth and sixth. There are so many other types of intermolecular attractive forces. But our attention goes only for three things. Van der Waals forces, permanent dipoles, or hydrogen bonds. So let us try to focus on these three things and try to get the idea. First, we go to Van der Waals forces. Okay, before coming to this, I'll give a small discussion on this, some introduction actually. Okay. First one. All right. VWF. VWF means Van der Waals forces. Van der Waals forces. They are also known as ID forces. There are a few things to know. First one is they are the weakest attractions. They are the weakest attractions. And formed between, not between, formed between non-polar molecules. They are the weakest attractions formed between non-polar molecules. Strength increases when the number of electrons and the size of molecules increase. Last one. These bonds can be broken easily at low temperatures. This is about ID forces. These are a few important things you should never forget. This is about ID forces. Now I go to the next one. Next one is hydrogen bonds. I'll discuss them in detail, but then before that, some idea. Hydrogen bonds. Now, under ID forces, we talked about them as a weakest attractions. But here, hydrogen bonds, they are the strongest intermolecular attractions. Intermolecular attractions. They are the strongest intermolecular attractions. Van der Waals forces are formed between non-polar molecules. Hydrogen bonds are formed by molecules that have hydrogen nitrogen, hydrogen oxygen, and hydrogen fluorine bonds. Okay, if a molecule has hydrogen nitrogen bonds, hydrogen oxygen bonds, and hydrogen fluorine bonds, then they can make hydrogen bonds. And then we say strongest intermolecular attractions. This part is not resolved for us. Next one is these bonds can be broken. No, these bonds cannot be broken. Can be broken easily. In other words, they break at high temperatures. I didn't say high temperatures, but high temperatures. Those are the basic things. It's better if you take down this van der Waals forces and hydrogen bonds, the notes into sticky notes, and paste with the tube, please. I could not write one important sentence here. That's there. Okay. Formed between non-polar molecules. Fine. This work is over. I will explain to you first how these VWF or van der Waals forces are formed. In other words, instantaneous dipole, induced dipole, attraction formation. How are they going to be formed? I said these van der Waals forces are formed by what sort of molecules? Non-polar molecules. Here, underline these non-polar molecules. I'll try to explain to you how these van der Waals forces are formed between non-polar molecules. Earlier, I told attractive forces are formed between molecules having some polarity. Now I'm telling that they are formed between molecules which do not show polar molecules. So I can explain it in this manner. By taking, I normally take 3 molecules for the explanation. So this is a molecule. One molecule here. Another molecule. Nucleus, nucleus, nucleus. These are non-polar molecules. These non-polar molecules, or any molecule you want, contain electrons, and these electrons show, constant movements. Electrons do not stay in a particular place. Electrons always move here and there. Just imagine if you think about the electron distribution in the middle atom. When electrons move here and there, if the electron concentration gets higher to the right-hand side, this red line shows how electron density is arranged now because of electron movement. Don't ask me why electrons move in this way. Electrons have energy, so they move. So if I remove this black line shows how electrons were distributed in the space earlier. But because electrons get concentrated in movement to the right-hand side, the middle molecule takes a picture like this. Do you see this? Now it is different to what you saw earlier. This is something that happens very suddenly, and as a result of it, you get delta negative charge here and delta positive charge here. And no one does it. This charge separation is not forced by anything. It just happens because of electrons' movement, random movement. So what I have shown here is instantaneous dipole formation. No one does it. It happens instantly. Instantaneous dipole formation. Instantaneous dipole formation. Okay. Now what happens afterwards? I'll go to the next stage. When electron concentration on the middle atom, middle particle, gives a negative charge on the right-hand side. Why negative charge comes to the right-hand side? Because electron density is higher in that area. Electron in this area is higher. As it happens, the electron density on the left-hand side of the right-hand side molecule get pushed a bit towards the right-hand side. It means its electron concentration gets distracted in this manner. Why a polarity came in the middle atom earlier? Randomly, is an instant occurrence. As it happens on the right-hand side, electron density is distorted because of the high electron density on the right-hand side of the middle atom. Electrons on the right-hand side get pushed to the right-hand side. Likewise, see now the electron density has changed. We have delta negative here and delta positive here. When the electron density on the left-hand side in the middle molecule decreases, electron concentration is less. From the left-hand side molecule, electrons come towards the right-hand side. Now this green line shows the new electron density. Now here we have delta negative and delta positive charge separation. What has happened here? We had to say induced dipole. See, in the middle one, we have instantaneous dipole formation. In the last one, we have induced dipole formation. So when the dipoles are formed in the middle atom and in the atom on either side, what is the next thing to happen? When positive and negative particles come closer to each other, there will be intermolecular attractive force formation. Here and here. Actually, these are the attractive forces named van der Waals forces. In other words, ID forces. You can take a picture of it. You can take a snapshot of this.